Welcome back, students. Now that we have described the bulk properties of systems based on their molecular partition function, we turn our attention to the motion of molecules. We care about molecular motion because molecules must move and collide with each other in order for them to react. We'll begin this process today in describing chemical reactions by discussing the kinetic theory of gases. So for today, we are going to review the Maxwell-Boltzmann distribution of molecular speeds. Today, we're going to describe the kinetic theory of gases. We'll be able to describe this model and defend the assumptions made in this model. They're pretty reasonable assumptions. And then what we're going to do is be able to calculate the velocity of a molecule. We'll first describe a speed distribution, and then we'll look at some benchmark speed values you can see here. And these are values that's useful to use to compare the speeds of molecules. So we'll look at the most probable speed, the average speed, and then what's called the root mean square speed of molecules. The kinetic theory of gases envisions gases as a collection of particles. In gases, we assume that each gas particle is isolated. Is this a good assumption? We can do some calculations by looking at the diameter of a random atom. We'll choose argon. The diameter of an argon atom is about 0.29 nanometers, which means the volume of that argon atom is about 0.013 cubic nanometers. At room temperature, 1 mole of an ideal gas, of which argon is 1, occupies 24.4 liters. If we divide this by Avogadro's number, that gives us 40.5 cubic nanometers per particle. In other words, you could fit over 3,000 argon atoms in the space that's only occupied by one atom. So this means that clearly each individual atom of our ideal gases is essentially isolated. And this is going to be true for basically all pressures and temperatures that these will encounter under normal conditions. We can therefore describe gases as essentially non-interacting particles moving freely through space. They will rarely encounter one another, which would result in a collision. We can describe the motion and collision of gas particles with Newton's laws. This is appropriate for essentially continuous translational degrees of freedom, which is what we have for translation. Already at the start of the semester, we used the kinetic theory of gases to predict the ideal gas law. You can go back to the first lecture recording if you want to review that. Today, we will use it to determine the speed of molecules. For our discussion the past few weeks about statistical mechanics, it should be clear to us now that there will be a distribution of velocities, since there's a distribution of energy. And of course, the energy of a molecule is equal to 1/2 its mass times its velocity squared. So a distribution of translational energy gives a distribution of translational velocities. We will begin by attempting to identify the velocity distribution function in one dimension. We have already noted that translational energy levels are essentially continuous, which means that essentially all velocities will be possible for these particles. We next assume that each translational degree of freedom is independent from the others. With this, we can come up with a velocity distribution. We'll use capital omega for the overall velocity of the molecule in all 3 of its dimensions, and it's a sum. It's based on the 3 different dimensions. So we're going to have velocity in the x, y, and z dimensions, and there's nothing linking any of these motions. So the particle will move in one velocity in the x dimension, and that can move in any velocity in the y and z dimensions. We've done this sort of thing before, way back last semester. So if we have 3 independent degrees of freedom, the function is a product of these functions. So our overall distribution for velocity is likely the product of 3 individual components in each of our 3 cardinal directions. With this distribution in mind, we can take the natural logarithm of this distribution to separate the 3 terms and the product of 3 individual terms. To do this, we have assumed that the direction of motion does not affect the properties of the gas. That is, the omega function depends only on the speed, not the individual components. With this in mind, we can take the derivative of this speed distribution with respect to one of the components of velocity to determine the distribution of that one-dimensional velocity. So what we're going to do is take the partial derivative of the natural log of our omega function with respect to, say, Vx. And we just kind of choose this arbitrarily. And we'll keep the other velocities constant. Well, what does this give us? We can take the derivative of these natural logs, and only one of them has Vx dependence. So this is simply equal to the derivative of the natural log of our function based only on the x velocity with respect to the x velocity. We can use the chain rule, and the chain rule will manipulate our derivative of the natural log. So we can turn this derivative of the natural log of omega with respect to only one dimension. And so what that will get us, to do that with the chain rule, we also have to take the derivative of the speed with respect to our one-dimensional velocity. So here we get an expression that will allow us to actually figure this problem out. And to be proper, these here should be converted into regular derivatives, whereas this is now a partial derivative. So can we evaluate the derivative of the speed with respect to one of the components? Of course we can. That's pretty straightforward. So the speed is simply the square root of Vx squared plus Vy squared plus Vz squared. This is basically the magnitude of a vector. We've done these sorts of calculations before. And so if we want to take the derivative of this with respect to V sub x, we use the chain rule again. So here we have Vx squared plus Vy squared plus Vz squared. We take that now to the negative 1/2 and multiply that by positive 1/2, just doing our normal derivatives. And then the derivative of the interior is simply 2Vx. So our 2 cancels with the 1/2, and that gives us Vx over the square root of Vx squared plus Vy squared plus Vz squared, which is simply V. So we can substitute Vx over V into this expression here. And that gives us that the derivative of the natural log of our speed function with respect to speed dv multiplied by Vx over V is equal to the derivative of the natural log of our one-dimensional function with respect to speed, or the velocity in that direction. Now, we can then rearrange this and bring the Vx to the other side. And so in doing so, we will get d natural log of omega as a function of speed over V dv is equal to d natural log of our one-dimensional velocity times Vx over dVx. Importantly, we haven't really chose x for any real reason here. So this is also equal to the derivative of the natural log of our y velocity function. And it's also equal to the derivative of the natural log of our z velocity function. All of these things are arbitrary. We only picked Vx because it was the first one. So all of these functions are actually equal to each other. What does that mean? Here we have 4 functions that are all with different variables, although this one is related to all the other ones. But we have these 3 functions with 3 different variables that are all supposed to be equal to each other. We've seen this last semester in quantum mechanics, and remember, when we see something like this, it means that all of these functions must be equal to a constant. And we choose that constant to be negative gamma. The negative there comes from reflecting that this has to have a finite probability under the curve that we're going to get eventually. So it has to be a negative number. So then we have a different equation to solve. Now we've removed this speed component, and every single one of these derivatives is equal to negative gamma. So we can say that the derivative of the natural log of our one-dimensional velocity function, and here we change notation a little bit. We just say v sub j because it doesn't matter which dimension we're considering. It's true for all of them. Over v sub j dv sub j is equal to negative gamma. And we can rearrange this as well to say the following. So instead of taking the derivative of the natural log of the function, we'll convert that into the derivative of our function, so df, and then we get df of v sub j is equal to v sub j f of v sub j times dv sub j, and this is equal to negative gamma. We can rearrange and integrate this expressions by leaving on the left-hand side all the functions of this velocity and putting the velocity terms on the right-hand side. So what that gets us is d of f of v sub j over f of v sub j is equal to negative gamma v sub j dv sub j. Then we simply integrate these here. The integral of df over f is simply the natural log of f, so this gives us natural log of f of v sub j. And then the integral of our right side of the equation is simply minus 1/2 gamma v sub j. So to get rid of the natural logarithm, that means that we have our function of v sub j is equal to a, the normalization constant, e to the negative gamma v sub j squared over 2. And with this function, we are almost ready to describe the speed distribution, or the one-dimensional velocity distribution. To finish this derivation, we need to identify the constants a and gamma. We have these two constants that we don't quite know what they are. To solve for a, we simply need to normalize the distribution to ensure that the total area under the curve is equal to 1, because this is essentially a probability distribution that tells us how likely particles are to have certain speeds. And so to do that, we can simply take the following integral. We'll integrate from negative infinity to positive infinity of a e to the minus gamma vj squared over 2 dvj, and to normalize, we'll set this equal to 1. We can use the rule for even functions to say that this is equal to 2 times the integral from 0 to infinity of e to the minus gamma v sub j squared over 2 dv sub j. And going ahead and solving this integral here gets us a times the square root of 2 pi over gamma. So rearranging this gives us a equals the square root of gamma over 2 pi. And this is our solution for a. To solve for gamma, we need a point of reference. We'll obtain that by looking at the average velocity. So particles have an average velocity, and we can write that as Vx. And we're actually going to look at the square of the average velocity. Now, why are we going to do that? Well, because the square of the average velocity is proportional to the average energy. Of course, 1/2 mv squared is the kinetic energy of the particle. Now, why are we doing this? We're doing this because based on our partition function, we already know what the average energy is. We can represent the average energy as kT squared times the derivative of the natural log of the partition function with respect to temperature. Now, in this case, what's our partition function? We're talking about a one-dimensional translational distribution function. So all we need, translation in 1 dimensions, is the one-dimensional translational partition function. And we can look that up, we know what that is. So we can evaluate kT squared times the temperature derivative of the one-dimensional partition function, which is simply 2 pi mkt over h squared to the 1/2 times the box length a. So we've seen these sorts of derivatives before, and it turns out, just like we saw before, that the derivative of a natural log of a function is pretty easy, because we can use log properties to separate this out. So here we can say this is equal to kT squared times the temperature derivative of the natural log of t to the 1/2 plus the temperature derivative of the natural log of all this other junk that's not t. And all this other junk that's not t is not dependent on temperature. So it has a temperature derivative that's equal to 0. Now, this term over here has a temperature derivative that's simply equal to 1/2 times 1/t. So putting those two things together, we get that 1/2 mvx squared is equal to kt squared times 1/2 1/t, which is equal then to 1/2 kt. Comparing these two things, we're comparing 1/2 mv squared to 1/2 kt. We can see that the average energy, the average square of the velocity in one dimension is simply equal to kt over m. Now, how is this useful? Well, we can actually evaluate what the average square of the velocity is, and we do this in a way that's very similar to what we're familiar with from quantum mechanics. If we want to know the average square of the velocity, we should know that that is kt over m. And we also know that that's equal to the integral from -infinity to infinity of our function multiplied by the square of the velocity operator. So we simply integrate this function here. And with this, we can figure out what the average square of the velocity is. So to put a in, we get this is equal to the square root of gamma over 2 pi times the integral from -infinity to infinity of vx squared e to the minus gamma vx squared over 2 dvx. And we can solve this integral if we want. We look it up in the back of the tables of our books. And this gives us gamma over 2 pi times 1 over gamma times the square root of 2 pi over gamma. So here our gamma over 2 pi cancels with our 2 pi over gamma, and that gives us that the average velocity, kt over m, is equal to 1 over gamma. So we're rearranging, we find that gamma is equal to m over kt. And that makes a equal to m over kt times 2 pi, the square root of that here. And so putting these two things together, we have that our velocity distribution for one dimension is simply equal to the square root of m over 2 pi kt times e to the minus m vx squared over 2 kt. And this is in terms of individual atoms or particles. It's often easier to use molar masses and so forth. So this is also equal to the square root of m over 2 pi rt e to the minus m vx squared over 2 rt, where m is the molar mass. Now, to get these things to work out still, it's the molar mass in kilograms to balance out the units there, but it still ends up working. So with this, we have an equation that's nice, and we don't have to actually calculate the individual mass in kilograms of the various particles there. We can just use the molar mass. Let's go and look at what these velocity distributions are so we can see some things about them. So going back to the slides, we can see some velocity distributions and note a couple things. First, we can note that the colder the particles are, so here we have one particle at 298 Kelvin and one at 1,000. The colder the particles, the narrower the distribution. And a narrower distribution means overall slower movement. Our particles are less likely to have very large speeds. We can also see that the heavier the particle is, so krypton has a much narrower distribution, overall moving much slower than either argon or neon. So the heavier the particle, the colder the particle, the slower the particle moves. And this is pretty much what we would expect from sort of classical mechanics. Another interesting thing to note is that these guys are moving pretty darn fast. So looking at neon, we have a significant population of neon atoms that are moving near 1,000 meters per second under normal temperature conditions. And of course, heavier particles will move slower. Also note another thing, and we're familiar with this from quantum mechanics, but the average velocity in the x direction is 0. Does that mean that the average particle is not moving? Of course it doesn't. What it really means is that our particles are moving equally likely in either direction. And so on average, their x component is 0. And even if we have a particle that has 0 motion in the x direction, which is possible, it still is moving in the y and z directions. For this reason, it's usually more meaningful to investigate the molecular speed rather than any of the individual velocities, or certainly the overall velocity, to see how fast the particles are actually moving regardless of direction that we're not so interested in. We can determine the particle's speed by essentially multiplying each dimension together. So what we can do is take a function of just the regular v here, and v is now the speed, this function of speed and with dv there, and this is simply equal to the product of all of our individual dimensions of x, y, and z. And this, of course, comes with a dvx, a dvy, and a dvz component. Just like converting from Cartesian coordinates to spherical coordinates, we're basically doing that here. And we go from a one-dimensional speed function or velocity function into a three-dimensional speed regardless of dimension function. So our dvx, dvy, and dvz here become 4 pi v squared dv. And this, we have to include this to make sure we're properly accounting for the fact that we don't really care about the dimensions here of our velocity distribution, which we're converting to speed. So what we get then is that our speed function is simply equal to the function of the velocity in the x dimension, and the function of velocity in the x dimension is simply this equation that we have up here. So it's equal to the square root of m over 2 pi kt e to the minus mvx squared over 2kt. And then we have this for the x dimension, and we have the same thing for the y and z dimensions. So I'll go ahead and paste this in here. We have another component. This is going to be from the velocity in the y dimension, so we can erase that x there and put a y, and we'll have one more for the z dimension. So we'll have velocity in the z dimension here. And then we can't forget to use our 4 pi v squared. So we'll go ahead and put that in. I'll just move all of this out of the way. And we'll go ahead and include this 4 pi v squared. And this is our speed distribution that doesn't take dimensionality into account. And when we do this, what we'll end up with, we can put all of our e terms together. And in our e terms, that's going to end up giving us a vx squared plus vy squared plus vz squared. And that is simply the speed of the particle. So doing that, we end up with an expression that says our speed distribution is equal to 4 pi. I'll group these terms here. So we have m over 2 pi kt raised to the 3 halves. Then we have our v squared e to the minus mv squared over 2kt. Now, just like we had before, if we would like to, and we often will like to, we can replace both instances of lowercase m with a capital M, the mass in kilograms per mole, and then replace both Boltzmann's constants with gas constants R. And this is the same equation that we had before. Sometimes it's just easier to calculate the mass in kilograms per mole rather than straight kilograms. And so we can use either one of these equations. With this equation, we can pretty easily see that the velocity distributions are not centered at 0. So when we convert it to speed, we now have our Gaussian function multiplied by v squared. And so this gives us an expression that is not centered at 0. And we can go ahead and go back to the slides and check out what these functions look like. So here we can see our distribution functions, and we can note the same things are basically true for these as they were for velocity, although we're not centered at 0. So here at higher temperatures, the distribution narrows and shifts to higher speeds, which is easier to see in these sorts of functions. And also, the smaller the molecule, the more shifted towards higher speed. So it's, again, the same sorts of things that we saw for the velocity, although it's just a little bit easier to see that most particles are moving at speeds. Now, are there some moving at zero speed? Probably a very small percentage. We could calculate the likelihood of that. But most molecules are going to be moving faster, and they won't only hit zero when they collide with a certain other molecule. There's actually an experimental method that has confirmed the Maxwell speed distribution. The way this method works is that gas molecules are heated in an oven with a small aperture, and these gas molecules that are heated in the oven go through this aperture with whatever speed that they have at whatever temperature they're at in the oven. As they go through, they come out of this aperture and they encounter these spinning disks. These spinning disks have slits that are offset, and these disks are spinning. So what's going to happen is that only molecules that pass through this first slit and hit the next possible slit after it's rotated all the way back around will actually be able to pass through. So this is a speed sensor that senses what kind of molecules pass through, and then there's a detector over here. And so with this kind of experiment, you can detect what velocities and how likely a molecule is, how many molecules or particles have a certain velocity based on this sort of sensor. And it basically exactly matches the predictions from the Maxwell-Boltzmann distribution. So again, pretty remarkable that our statistical mechanics are able to basically exactly predict the speeds that gas molecules have. We'll close today by looking at benchmark values for the speed distribution. Since all of our distributions have the same shape, we can go back here, and they all have essentially the same shape, the same functional form, just different masses and potentially different temperatures. We don't actually need to use the whole function, but we can just use certain benchmark values, certain parts of these functions to compare them. Benchmark values that we most often use are one of the following three values. We use the most probable speed, the average speed, or what's known as the RMS speed. So the most probable speed is simply the maximum of the speed distribution, which is going to be the derivative of the speed distribution with respect to speed, and then we set that equal to 0. Then there's the average, which is, again, the average speed. We can calculate that by multiplying the distribution by the velocity or the speed, and then taking the integral of that, just like we found the average position for quantum mechanical, electrons and so forth last semester. And then lastly, we have this RMS speed. The RMS speed is a little weird. It's a statistical value, and the RMS speed is the square root of the average square velocity. So we do what we did before and take find the average square of the velocity by multiplying our speed distribution by the square of the speed, and then that gives us a value. We take the square root of that value, and we can go through all the math in class if you're interested. Essentially, we have these three increasing numbers. So here we have the square root of 2 times RT over M, the square root of 8 over pi times RT over M, and the square root of 3 times RT over M. So these are increasing, and they always fit at the following benchmark value. So the most probable velocity, the most probable speed is this highest probability here. The average is shifted a little bit to higher speeds, and the RMS is shifted even a little bit more to higher speeds. And for a point of comparison, 400 meters per second, which is about the most probable speed here of argon at room temperature, is about 900 miles per hour. So these guys are going pretty fast. And we can sort of envision what's going on here. All of these particles will have different speeds, and they will collide with each other, which changes their speed based on collision. We'll talk more about collisions and so forth in the next section.